And such that if you are trying to get back to what I'm saying, you can go to my YouTube channel then to finding the clip. Okay, so last time we talk about the U and VUE. We end up here, and then I want to emphasize that again. Then for you guys to working on homework, and then later on we are going to move on to the hypothesis testing, and then cover meter number 2. And I think next week we are going to meter number 2, and this Thursday I'm going to posting the past exam, so meter number 2 it's for you guys to do practice. And then next Monday we are going to go through past exams in the discussion time. Okay, so we end up here U and VUE. Okay, so I think there are only 2 methods right now for us to find U and VUE. Basically, it's the first one is let me pull out my. Okay, so the first method right here. Okay, hold on. The first method right here is that you find unbiased estimator first. Any unbiased estimator is W for tau theta. If you remember, I told you that this unbiased estimator could be lousy, could be anything. Very easy estimators as long as it's unbiased. And then you are finding the complete sufficient statistics. This is very important. As you can see in the later method number 2, you also find some complete sufficient statistics. So for knowledge, whenever we're trying to find the U and VUE, we always trying to find complete sufficient statistic first. Okay, then the difference would be from method number 1. It's okay. I have my W unbiased. Then I'm working on 5T right here, trying to deriving expected value of W given the complete sufficient statistic is. Okay, it may not be easy to derive, as you can see later on example, but that's all we can do. Okay, then by doing so, we can using Lehmann-Schaffer to claim that it's this guy phi t is a U and VUE for tau theta. Okay, then another one is you working on any statistic complete sufficient directly. Okay, either working on the phi t. Usually, we actually only working on t only. For example, again, I'm saying a lot of times it's if t actually is a complete sufficient statistics, then you're working on the expression of t, and then cross your fingers. Eventually, it's a plus b tau theta. Okay, if you're lucky to get it, then we always put t minus a divided by b right here to become unbiased estimate of tau theta. Unbiased estimate of tau theta. And then by Lehmann-Schaffer is because t is complete sufficient statistics. So by Lehmann-Schaffer, I can also claim t minus a divided by b is the U and VUE. Okay, that's the most easy one to find U and VUE, I think. Of course, if you do know some phi t right here, okay, phi t right here, then if it turns out to be still a plus b tau theta, then you just working on your algebra to find out phi t minus a divided by b as a U and VUE for tau theta. Okay, there's 2 ways we can find it. Okay, this is example. We stop right there. Okay, now we have x1 and xn. It's RID follow Poisson theta. Okay, first one is you show that indicator function of x1 right here. Okay, what I'm saying lousy is what? You do have x1 to xn. Okay, but unbiased estimator, I can only using x1. It's good enough. Okay, that's why I call it lousy estimators. I only use information of x1s. Okay, then how do I show that's unbiased then? Right, unbiased estimator of E minus theta, right? Going with definition, right? Do expectation, okay, of my estimator, trying to show that it's unbiasedness. And then this is indicator function. This is binary, right? As I keep told you that it's only choice of distribution of binary is what? Penalty. And then expected value on indicator function right here, nothing but probability. Okay, nothing but probability of x1 equal to 0. Then because it's a Poisson, so x1 equals to 0 is what? So you have x factorial, lambda x, lambda theta right now, lambda x, then e minus lambda. So it could be really easy to show that probability of x1 equals 0 is e theta. That means expected value of statistics is unbiased of exponential e theta. So easy to show that indicator function of x1 equals to 0 is an unbiased estimator. Then using method number 1, okay, you are trying to find complete sufficient statistics, right? Easy to show that because of exponential family. Okay, so you work on it, you will know that summation xi is complete sufficient statistics. Then by the Chavez, right? Given complete sufficient statistics, deriving expected value of your unbiased estimator. Then by using that way, you can find a UMUE for E theta. But this guy right here equals to what? Not necessarily easy. But for this example, it's easy actually. Not necessarily hard. Okay? Derivation is right here. It's okay. You do have this guy right here. Okay. Summation xi, I from 1 to n, xi. You need to ask yourself follows what? Right? Xi each follow Poisson. Xi Poisson theta. Then summation xi, you can looking at the distribution sheet of Ken-Sauberger, you will know that it's Poisson and theta. Okay, and then if you know that, again, expected value on indicator function, nothing but probability, then their indicator variable then. Okay, then this guy becomes conditional probability problem, right? Conditional on this guy, then calculate probability of x1 equals to 0. Okay, then I think it's standard drill then, right? Conditional probability, you have your denominator as a marginal, as a conditional, then your numerator is what? Joint distribution between x1 and summation xi equal to t. Okay, so right here, because of Poisson, this guy right here, right? Summation xi equals to t, because of Poisson and theta right now, Poisson and theta right now. So that means I have t factorial lambda become n theta, right? Wow, n theta. Then lambda x right now is t, right? Then exponential minus n theta x, right? That's what the probability of the random variable equals to t. That random variable follow Poisson and theta. Okay, then the numerator would be a little bit tricky, but it's handleable. The reason for that is, okay, where is, okay. The reason for that is, you do have x1 is 0, okay? Summation xi is t, so I can basically write it summation I from 2 to n, xi equals to t as well, right? x1, 0, so that means x2 plus x3 plus until xn is t. The reason I want to write that is I can then use an independence assumption. For example, x1 independent with x2 to xn right here. So then I can write as a product of x1 equals to 0, then times summation I from 2 to n xi equal to t separately. That means I'm using the probability of is a property of x1 independent with x2, then dot 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 to xn right here. Okay, so then because of Poisson, I do know what probability of x1 equals 0 is, right? Again, right here it's 0 factorial, then lambda 0 e minus lambda. Actually, we know that already, equals to e minus theta. Okay, then how about summation I from 2 to n, then xi then, right, equals to t right here. Then because I do know this guy is right now is Poisson, then n minus 1, then theta, right? So summation I from 1 to n xi Poisson and theta, summation I from 2 to n, because I only have n minus 1 Poissons, so Poisson n minus 1 times theta. Okay, so then right here is I do have t factorial. Right now the lambda become n minus 1 theta, then with t lambda x, right? Then e minus lambda, so lambda is n minus 1 times theta right now. Okay, so then you do have this probability, this probability, this probability. Then you can see a bunch of things cancel out. Then let me see if I have a space to show that in the board. Otherwise, I need to use a whiteboard. It's not really easy to switch the monitor right now. So let's take out something I have already. Okay, so that's working on this corner right here. Okay, so that means this guy right here equals to what? I do have this probability, okay, right here. It's n theta, then t, then exponential minus n theta, then divided by t factorial. Okay, I do have this probability right here. It's e minus theta. Okay, I also have a probability right here. Is what? N minus 1 theta, then t, then exponential minus n minus 1 theta, then divided by t factorial. Okay, then I'm looking for a bunch of things canceling out. Then. So this guy cancel out, I can see. And then this guy minus n theta, this guy right here become e minus theta. So cancel out, and cancel out as well. Okay, and then I bet you do have t outside, and the inside would be n minus 1 divided by n, right? If we put t right here, I can have the overall bracket, and then putting down denominator n minus 1, numerator is n. Okay, so then that's exactly the same thing as I have answer right here is t. Check. Okay, good. So that means we divided that phi t, or basically is a phi summation I from 1 to n xi. Okay, then you plug in replacing t right here as a summation xi. Okay, so then by dimension phi, I can claim that this guy is a UMVUE. This guy is a UMVUE of the exponential e theta. Okay, good. So in the midterm, I'm more than likely to asking you it, hey, how do I show that this guy is unbiased directly? This guy looking so weird, I think, right? So it's not like a regular function VOC. Then how do you proving that? How do you prove that that guy is actually unbiased estimator then? Okay, so it's not actually that difficult if you know how to handle expectation. So say right here, oh, hold on, okay, good. Come back. Yeah. Expectation. Hold on. Okay. Expectation right here. You do have your 1 over 1 minus n, then summation xi right here. Okay. Can I actually directly show that this guy is exponential minus theta? How do I show that? Okay. So really just using the properties of expectation, right? Okay. This guy is still function of n, function of summation xi. You got to know that first. This is function summation xi. So that means inside guy is the g function of summation xi, then what kind of expectation is what? I can actually using summation xi as PDF. Right now it's Poisson and theta. So that means this guy, it would be it's what? Again, I can say t from 0 to infinity. Then 1 minus, this is function of t, function summation xi. Okay? And then times what? Times PDF of Poisson and theta. This guy is what? This guy is t factorial and theta. T exponential minus n theta. Okay? Again, inside expectation is a function of a random variable I do know about the distribution of, right? I do know summation xi follow Poisson and theta. So that means I can use this guy's PDF of Poisson and theta. Then times a function as a definition of a PDF then. Okay? But the point is, how do I handle that? Right here, the summation. I need some space. So, well, oops, okay. 1 minus n right here. And this guy is t factorial, t from 0 to infinity, right here. Okay, good. Then how do I handle that then? Okay, so right here it's, let me see. I think basically you're looking for what? You're looking for creating another Poisson distribution. That's my goal. So I'm going to write t factorial. I'm going to write this, hold on, come back. So this is t, this is t. So I can basically combine it together, become n theta, then minus theta, then t. Right, n theta minus theta t, I think so. Then exponential minus n theta then, right here. Okay, good. So that means I'm looking for what? I'm looking for it. Okay, pardon me on that. Let me, I don't have space. I need space. Let me right here. Okay, so right here is summation t from 0 to infinity. I'm looking for creating another Poisson distribution, which means that it's, I can basically, could you guys see that? I can basically treat this guy right here as a new lambda. Okay, so it means if I write that n theta minus theta, then t, I can purpose creating this guy is minus n theta minus theta. Right? I'm creating another Poisson distribution, but the point is how much do I sacrifice? Right? It turns out to be, let me see, it's minus n theta right here, right? Minus n theta. Yep. So then I do creating another extra exponential theta. So I need to compensate that this guy becomes times e minus theta. Okay, such I can go back to original equation right here. Okay, so then it's obvious to me right now then. Why? Because this guy is what? A new PDF. Okay, I should say it's more like inside guy's new PDF. Oops. Okay, so inside guy is more inside guy is new PDF, right? Use summation over the domain of PDF, whole thing nothing but equals to 1, then eventually E minus theta. So that's how you prove your weird statistics is unbiased estimator of exponential E minus theta. Okay, good. So any question on this? Okay, do we need to calculate expectation? I think this should equal to how many are you asking what? Is how many there?
Yeah.
Yeah.
I don't think we should calculate this expectation because I think
Which one? Which expectation?
This complicated expectation. The expectation of 1 minus 1 over n to t.
Are you talking about A or B?
Just
one or two?
No, just the last part you calculate. Just next slide.
Next slide right here.
Yeah, right here. Yeah, the
Which one?
The expectation of 1 minus 1 over n power t.
Why not?
Because I think the expectation should be equal to the expectation of indicator of x1 equals 0.
You mean the whole thing right here?
Yeah. The expect.
I don't see that. Is that obvious? You're saying that this guy equals to expectation?
Yeah. Oh, indicator.
Oh yeah, I understand that. I understand what you're saying. You're saying that this guy should equal to the phi t. So it's automatically unbiased.
Yeah. Yeah.
Is that what you're saying?
Yeah.
Yeah, I know. I understand that. I mean, yeah. But I just want to show that it's how do you directly show that your statistics is unbiasedness.
Okay.
Yeah, of course you can use this result right here.
Okay.
To show that it's unbiasedness. Yes, you could, but it's not so obvious from this way. You will know this way, right? To me, it's not obvious. Okay. I just want to show another way of showing this. You could still directly showing that guy's unbiased of E minus theta. It's making sense?
Yeah, thank you.
Okay, yeah. Good. Okay. So as long as you have questions, just chat it, or you can actually, I think you can raise your hand, right? So in some way, you can actually show up. I mean, wave a little bit to me, and then I can. But I'm also looking at my board, so I'm not necessarily pay attention to you waving, but do it then to see if you can notice. Okay, great. So then, let me take this all out. Okay. So this guy would be really likely to happen in the midterm number 2, which is what? Which is how do you find MLE? How do you find MLE for exponential E minus theta? Right? So if you remember that, or you should remember that, is you could using your Poisson distribution to deriving theta hat is summation xi divided by n or x bar x. Okay? Then how do we claim MLE for function of theta then? Basically, E minus theta is nothing but say tau theta x. How do I find it? As MLE, easy, by using invariance property of the MLE x. That means MLE for exponential minus theta is nothing but exponential minus x bar x. Okay? Because theta MLE x bar, then MLE for tau theta is nothing but plug-in of where theta is, called invariance property. Okay, good. And then another thing would be it's interesting part right here is right. Okay. I would have that in the meter number 2 as well if the chance is correct, which means that it's if I give you some question in the flow, I think, yeah, it's a good question to ask. I might ask you for that as well because this covering meter number 1. So then how do I know? Okay, I have this guy right here. How do I know in convergence to what, right? When n goes to infinity then. Okay. Again, it's like I said, that you do have summation I from 1 to n is your friend. Okay. So because I could know that 1 over n summation I from 1 to n xi goes to what? Okay. Think about it. So I think most of you guys, you know, it goes to probability EX1. It's this guy using nothing but weak law of large number. Okay. So that means EX1 right here by Poisson is theta, I think. Okay. So that means this guy right here, if I can rewrite it, 1 minus 1 over n, then summation xi. If I can rewrite as 1 minus 1 over n, then have n right here. Actually, let me see. I have n right here. And then I purposely just taking out summation I divided by n. Okay? I purposely put n inside, then put n outside, nothing changes. Okay, good. And then I do know goes to where? Okay, really easily, because I do know this guy right here goes to P, then theta. Okay, then inside guy is a function of n as well. Function of n as well. And then if you remember our homework, okay, this guy right here as well. This guy is going to goes to what? There's no probability, only sequence. Goes to exponential minus 1 x. Okay? The whole thing is actually 1 over x divided by n. Then n goes to exponential x. Okay? Good. So inside guy goes to exponential minus 1. Outside guy goes to theta. Eventually go exponential minus theta. Exactly, which means that it's this guy not only a bus estimator, but also is consistent estimator as well. Consistency. Okay, good. Okay, and then also not only that, but also when you say MLE right here. Okay, we talk about say this MLE right here, exponential minus x bar is my MLE. I might as well asking what does that goes to then in P. Then again, it's I do know about x bar goes to P, then theta. Then what does this guy goes to? Nothing but exponential minus theta. Okay, that means both convergence to the target parameters tau theta we are looking for. This guy also consistency as well, right? Exactly told you that it's, hey, I do have this unbiased estimator look weird. Okay, I also have this estimate MLE look much more clean. Okay, then both are consistent estimator of exponential minus theta. Okay, so my question to you is, think about it a little bit. I do have two estimators. Estimator number 1, okay, unbiased, consistent, and I have estimator number 2, MLE, right here. Okay, good. Then emitter number 2, I'm going to ask you it. Which one have smaller variance? Which one? Okay, no doubt it's going to be U and VUE has smaller variances. Okay, good. Any question on this? If not, we are going to the hypothesis testing then. Okay, good. So let me close this out. I'm trying to pull out my screen about, oh, this deal there again. Okay, so let me see where, okay, good. Where's my first slides? Okay, more estimation. Okay, so we are going to talk about chapter number 8, okay, Sauberger hypothesis testing. Okay, this is a fun section, and then I always like having a lot to say about this testing section because this idea got challenged recently because of p-value things. Okay, so when I teach this, sometimes we have to trigger up discussion, but I don't see you right now, so I don't know how to discuss this with you. So I'll go through it, and then if you do have this kind of if you have any idea about this, I'm saying it's you saying, well, it's totally like making no sense to you, then I agree. Okay, especially your patient, then oh, it's fine. Then we can talk about it to see the idea of the difference between it's more like a frequentist approach versus Bayesian approach. Okay. Anyway, okay. To understand, if you are Bayesian, it's good for you to know what frequentist thinks about this section. Okay, good. So I think most of you know that already because the p-value things have been used for us for a lot of times. So then our class is definitely to be okay, how do we write it more formally in a way we are trying to looking for? Okay, how do we write things mathematically when you do testing? Okay, we know the idea, but how about mathematical approach it? So let me do some introduction first. Okay, so we see that a lot as a presentation is you have like treatment, right, for disease. Then you do have standard treatment. Okay, let me see. Okay, you have standard treatment right here. You have standard treatment right here. Then having a successful probability is 0.7. Okay, then you are trying to develop a new drug, trying to see whether or not the successful probability is theta. Okay, you don't know how good the drug is. Then you collect your data, you do experiment, you do the clinical trial, you collect the data. Then eventually we are going to do one thing is do testing. Okay, the null hypothesis is going to be whether or not theta is more than 0.7, 70%. So if I do have evidence to show that my alternative is true, I rejected my null hypothesis, then I'm basically claiming that my drug is successful. Successful rate is better than 70%. Okay, so that means the hypothesis is the statement about the population parameter. Okay, good. Then mathematical speaking, statistical speaking, I do divide it by parameter space into two disjoint sets. Okay, one called null space, one called complement space right here. Okay, good. So theta will be overall space. Then this guy would be null space. Okay, good. So then the null hypothesis would be my H0 theta belongs to null space. Then compared to my alternative, my theta belongs to complement space. Okay, easy. Okay, and then in this class, it's really important to tell what the space division would be. Okay, so that means when we talk about null versus alternative, we are going to identify how large of the parameter space under null or under alternative. The first one is so-called simple versus simple, which basically means that it's this guy null space having only single points, and then alternative also single space. That means it's simple versus simple. And then simple versus composite basically is what my null space have single points. Okay, but there are many points, right? Interval 1 false to 1 right here. Any point right here is belongs to my alternative spaces. Okay, yeah, by the way, we always using theta 1, okay, to describing alternative spaces. Then composite means a lot of points right here in my alternative space. Okay, then one-sided means that it's this guy always bigger than 1/4. Okay, called one-sided. Then simple versus composite, two-sided. Right here, this guy single point, and this guy is what? I do have 2 times. I have a single one, 1/4 right here. I do have 1 and 0. I do have two-sided. 1 is here, then 1 is here. They are both many points, so composite, and then two-sided, right-hand side and the left-hand side, two-sided. Okay, of course you can have what? You can divide your perimeter space 0, 1/4 right here, and then this guy right here is your null space, and then this guy right here, left-hand side, I think one-sided, right? One-sided. No? Okay, yeah, two-sided, I think. Then that means right-hand side and the left-hand side all belongs to your alternative. It's, of course, the original perimeter space is from 0 to 1. I apologize. So let me make it clear. So suppose it should be this. From 0 to 1 is the whole thing is oval space. Oval space. And then you have that from 0 to 1/4 right here. This guy right here belongs to null space. This guy right here belongs to alternative edge. Okay. Then of course there are many points in null hypothesis. There are a lot of points in alternative hypothesis. That means composite versus composite. Okay. Of course you can read weird in a way of right here from 0 to 1/4. Okay, then 3/4 to 1. I mean, it's really weird, I think. But the point is, you don't have anything in between. You don't have this. So this is overall as well as a union. Okay, union. Okay, union. And then, of course, you can talk about this guy is your null hypothesis. This guy null space. This guy is your alternative. And again, it's you do have a lot of points here, a lot of points here, so composite versus composite. Okay, good. So really, it's just by definition of the space, perimeter space. By any means, is right here. It's we are doing hypothesis testing. We are basically divided our perimeter space into several parts. Could be single point, could be composite point sets. Okay, so let me introduce really important mathematical notation, so-called test function. So when we do hypothesis testing right here, basically we are using data, right? We collected data to decide whether or not to reject it null hypothesis. Okay, this term is very critical. Okay, so when we do hypothesis testing, we always only talk about null hypothesis. Either we reject or do not reject. Okay, right? From your undergraduate statistics, your teacher told you that it's only thing you can say is do not reject. Don't say accept H1. Remember that? Okay. Yeah. So we are quite arrogant on it. Okay. Say do not reject. Don't say accept. Okay. Because we can talk about it, why can I say so later on when we have real things to talk about. Okay. Good. So then this kind of testing procedure is a rule that whether or not we are going to reject it null hypothesis or not. Okay. Only talk about null hypothesis. Okay. Then there's one mathematical notation, very important, is called test function. Delta x right here. That means delta x, right, is 1 or 0 or 1. Okay. 1 means reject null hypothesis. Then do not reject null hypothesis. It's pretty simple. Function of x. Then delta again is 0 or 1. It's binary. Okay, good. Let's call decision rule right here, right? If delta x is 1, null hypothesis rejected. Delta x is 0, null hypothesis do not reject. Okay, good. Then this kind of rejection decision region actually divides your sample space into 2 regions. Okay, called rejection region, basically where delta x is 1. And then if outside of rejection region, then your H0, your null hypothesis is not rejected. Okay, sometimes I myself as well as I'm going to switch. I don't know which one I will say which one, but you could either say it's rejection region or critical region. Okay, but I think rejection region possibly more straightforward to everyone. What do you mean by rejection of a null hypothesis? Then again, I say do not reject, right? But I still say accept the region right here. Okay. Yeah, sometimes it will be left. Yeah, sometimes Bayesian definite us. Okay, accept this region. But you say do not reject, right? How do you say accept the region? Well, it's fine, but it's nothing but complement of your critical region, rejection region. It's okay. So then by mathematical notation would be I might have rejection region, which is a sample, is a data, such that your delta x is 1. That's that easy. Okay. Of course, your complement of rejection region would be its delta x is 0. Okay. So I think you do know what type 1 error is right here. Basically, it's, I think you drew this kind of cross table before, right? I do have null hypothesis. I do have H1 right here. This guy is reject null hypothesis. This guys do not reject null hypothesis, right? And then null hypothesis true, you reject null hypothesis, then you make error right here. Right? Error. Null hypothesis true, you do not reject null hypothesis. This guy is correct, making right things. Okay. Alternative hypothesis true, you reject it, you do a right thing as well. And then alternative true, you reject it, you are doing the wrong thing right here. And then this guy is type 1 error. This guy is what? Type 2 error. Okay, good. Then we all know that what type 1 error is alpha right here, alpha. But I do want to point out which would be struggle for you in the next months would be it. In the undergraduate versus right as well, under null hypothesis, right here, under null hypothesis, I reject my null hypothesis, right here, type 1 error. We always write this, only alpha equals to probability is how we feel better about the null hypothesis, okay? But in this class, pay attention to one thing is, by saying we say so. But the point is, when you answer null hypothesis, you may have so many points. Remember composite null space right here, 1-4 right here, okay? You have so many data points, they have so many data in your null hypothesis, okay? By writing so, really not necessarily say everything about each point of data. So in this case, pay attention to its definition of type 1 error. It's actually, you need to pick up the largest one. That's what's the primum right here, place 2, okay? The largest one among data in null space. What is the largest error we can make under null hypothesis then? So don't forget about this term, okay? Let me emphasize that again. Which means it's the alpha we have, this guy really important, okay? As you can see in the future, it's this guy really important. We are trying to talk about one thing is under null space. What's the largest error we can make under null hypothesis? That's called type 1 error, okay? But type 2 error is the same then. Do not reject null hypothesis when it's false. Okay, the same thing right here, type 2 error right here. Okay, so far so good? Any questions on that? I'll give you 5 seconds to ask questions. If not, we are going to talk about next one, so-called like ratio test. Okay, yes. Oh, so far so good, thank you. Oh my God, I'm like a radio talk show host. Yeah, I don't like to talk to machine. Okay, good. Yeah. So right now we are talking about idea about hypothesis testing right here. How do we do testing in a frequentist way? Okay. Then right here it's, hey, if given any questions, could I actually using a general principle to find a test? Okay. I do know you guys, some of you guys using like a t-test, chi-square test a lot. Okay. Then yes, we do have so many tests right now in practice. Then, what if I do have a new question at hand? I don't find any currently existing testing procedure I could do. Do I have any general principle? Okay, general principle. To teach me that if I don't have any test at hand, I could do testing. By using this kind of general approach to derive a new statistical test. Yes, we do. The most easy one, the most generally used one is so-called likelihood ratio test, LRT. Okay. Then how do we use that then? What's the definition of a likelihood ratio test statistic is? So easy. Is write this lambda x right here. Okay. There's a numerator, there's denominator. Okay. Both are using what? Likelihood function. Okay. Likelihood, right? Likelihood. Okay. And then ratio, right? Ratio. You're doing ratio things. The difference would be your numerator is under null space. Theta belongs to theta naught or theta 0. Okay. Then your denominator is not alternative. Pay attention to that. Okay, sorry. Pay attention to that. This guy is null. Your denominator is what? Under overall space. Okay, again, numerator under null space, denominator under overall spaces. Okay, good. And then if you look at, you have finding some supremum under overall space, then you have like a function right here. What does that actually mean? You are nothing but finding MLE, isn't it? You are under overall space. And then finding that theta maximize, right? Supremum maximize your like function. So it's really nothing but finding MLE right here. Okay? Under overall space, easy, regular MLE. But pay attention to this guy also finding MLE as well, but under null space. Okay? So then that statistics would be easily constructed like this guy right here, right? Each one, numerator, denominator, all finding MLEs, but under different space. One under null, one under overall space sets. Okay? Then next one, you pay attention to it. Okay, if I do deriving lambda x as LRT, then how do I do testing? That means I finding critical region, okay, as x. Then this guy right here is my testing criteria. So say, if I collecting data, if I deriving lambda x right here, I'm going to say that smaller than some constant cutoff c right here. Okay, if lambda x smaller than c, I reject the null hypothesis. If lambda x bigger than c, then I do not reject hypothesis. Okay, there are several things to pay attention to. Number one is c value. C is from 0 to 1. Why C is actually from 0 to 1? Looking at your lambda x right here. Look at your lambda x right here. Okay, hold on. And imagine that what likely function means, right? That means how likely, right? And then you do have, when you find MLE right here, right? This guy, if there's no limitation, everything, this guy right here, if you what? Your theta had MLE right here. Okay? It's based on what? Overall space, isn't it? Say if somebody do this kind of things, hey, I only talking about this guy at null spaces. Okay, right here, null space. The largest one, of course, in terms of likelihood comparison is what? This guy is going to be this guy. Of course, going to smaller than the largest one over overall spaces. Right? Making sense? Okay, making sense? So this guy always smaller than this guy. So when you take a ratio, of course, your C would be smaller than 1. Okay, good. Okay, so that means, again, it's y smaller than, right? Again, thinking about what likelihood means. That means if under null space, this value is too small, right? It's very too small, such that it's too small until some value. You are going to say what? Well, null space is not going to happen. Okay, so if somehow, of course, you will write the whole thing in your cheat sheet, right? Oh, no, you don't have cheat sheet right now, right? You'll take a home exam. But really pay attention to, or at least think about it. Why is guy smaller would making more sense? Okay, there's no chance to become bigger. There's no chance to become bigger. Always smaller. Okay, but I don't have much time right now. So I do want to talk about some example because I want you to have something to know how to do that, yeah, on Thursday. Good. So again, it's summary is you're deriving your LRT statistic right here. You reject the null hypothesis smaller than C. Okay. But the point is, good point is, do I told you what C is? Okay. I don't told you what C is. You need to find the cell. You need to find the color of C by yourself. Then how do I find color of C then? Really important. How do I find C? Using this equation. Using your type 1 error to find color of C. Okay, because this is your test region, right? Okay, that means this guy is what? Under null hypothesis, I rejected by null hypothesis. That means what? Nothing but type 1 error. Okay, then again, definition of in all cases, you need to put supremum right here because you have many theta points. Okay, good. Then, of course, you do have rejection region right here. And then you of course you have like a accepted region right here. Very straightforward. Okay, good. And then the point is, well, right here is what? You might have bigger or smaller, okay, in terms of LRT test, okay. Then you will find out this guy right here. I'll teach you why at assumptions. This guy or this guy, really looking at what the direction of H1 is. You will see that. Okay, good. Let me, okay, we still having that 30 minutes left. So let me quickly move to this to told you what does that mean by LRT. So if we have x1 to xn to normal theta 1, okay, considering testing about null hypothesis, this guy is simple, right? Remember that, talk about that, simple. Then versus what? This guy right here, theta doesn't equal to theta naught. It's composite. Okay, good. Then we're just using definition of lambda x right here, right? One is finding the supremum theta under null space L theta. Denominator is theta under oval space L theta x. Okay, good, by definition. So right here, looking at this theta on theta naught, in the theta naught, you only have single point theta 0, right? Your theta naught basically is what? Only single point theta 0. So lucky you don't have any phi maximizer. You don't have any phi maximizer. Only single point, of course, they are maximizer. Okay, so that means right here, nothing but plug in L theta 0. Okay, then your denominator over space, right? Finding maximize ever theta, right? Is what? Nothing but x bar h. That means you do need to practice your how do I find L theta is x bar. Okay, let me jump. I'm not going to do everything for you right here, but based on x1 to xn is normal theta 1. You do need to show that. You do need to know how do I show MLE is x bar h. Okay, so it means by definition of RT, by these two guys, you find it, right? Numerator, denominator, then it's combined together. Okay, then this guy right here is nothing but L theta 0. Okay, then this guy right here, nothing but nothing but L then x bar h. Okay, good. So that means right here is what? So let me show that it's right here. Let me find a place to write. So of course, right, like a function. Let me write more clearly. So like a functions, theta in general is what? Is I from 1 to n, then square root of 2 pi, then theta 1, right? Theta 1. I think theta 1, so you don't have sigma square, then exponential minus 2 xi minus theta, then square, right, in general. So that means this guy nothing but 1 over square root 2 pi, then with n, then exponential, then minus 2 summation xi minus theta, then taking square then. Okay, good. So that means the first one, this guy right here, you plug in theta 0, you plug in theta 0 right here, theta 0, okay? Then the next guy right here, theta is x bar, you plug in where theta is. This is where theta is. Okay, good. And then you do that, expected. So you do that, you can see these two guys cancel out, right? And then exponential, then you have this guy right here from numerator, this guy right here from denominator. Okay, and then since right here you have this equation, okay, this equation also easy to show that it's okay. I have 9 minutes left, so I'm trying to push a little bit. Okay, if you do that, you will see what happens. Okay, I'm going to talk about it next week to see. I want to make sure that you understand why it goes out to be like this. Okay, so then say this guy eventually take on this guy. Okay, basically open up a plus b, you open up a squared plus 2ab plus b squared. You might remember I showed that in other lectures as well. Okay, say this guy right here, I want to take out, I want to see what happens right here. Okay, so right here is what? You do less, that means this guy and this guy cancel as well. Then this guy become that right here. Okay, right here. Okay, so that means this is exactly your lambda x, test statistics. This guy's LRT statistics. Okay, then again, like I said, we talk about it. To do the rejection region, is what? Nothing but put your lambda x smaller than c right here. Lambda x smaller than c right here. Okay, which can be written by this. Okay, written by that, it's okay. This guy right here is just taking log, then taking square root. Okay, again still. Do you know what c is? No, you don't. And then how do we find c? I will show next time is how do I find c using type 1 error probability. Okay, let me also finish this example, and then we can finish today's class at 1:45. Okay, again, LRT under the x1 to xn, okay, it's from exponential distribution with a PDF of this guy right here. Okay, good. Then basically x depending on theta. Very, very critical. You'll see what happens. Okay, good. So right now it's, if you're considering, of course, Laplace function right here, okay, Laplace function right here is what? Well, you might see me do thousands of times already, right? This is my PDF. But really don't forget about this indicator function right here. Let me write clearly, otherwise you just don't know what I'm saying. I don't want to be. So Laplace function right here, I from 1 to n, then exponential minus xi minus theta. Don't forget about indicator function to indicate where the range is. Then right here equals to what? Exponential minus summation I from 1 to n, then xi minus theta. Then right here, how do I show this, right? Then basically, as long as my minimum one bigger than theta, then I cover everything because I do know x1 to xn is going to be bigger than theta. The reason why comes here. Yep, okay, comes here, right? Theta smaller than x1 x. Okay, good. Say if I'm doing testing, now space theta smaller than theta 0, alternative theta bigger than theta 0, we actually we don't pay attention to alternative hypothesis. And then you are looking for, okay, 10 minutes left. I'm looking for lambda. Lambda, again, I keep writing that down, right? Numerator is under null space, L theta. Numerator under overall space, right here. Okay, good. So numerator, always easy. Nothing but find the MLE under overall space. And you should know that already. I think, hopefully you know that, how to find MLE right here. Okay, see right here is Laplace function. Oops. This guy, Laplace function. Okay, good. Oh, saying look at this, right? Look at this. Look at this. This is my Laplace function, theta x right here. And then this guy is my theta as a function of theta, right? You're asking yourself, this function increasing or decreasing function of theta? This guy increasing theta or decreasing function of theta, right? The answer is what? The answer is increasing function because you have positive term right here and theta. So the whole thing is the increasing function of theta. Okay, but this kind of increasing function would having that limitation, having that domain restriction at x1 right here. So say x1 right here, right here. Then look at this, right? Only theta smaller than x1, theta smaller than x1 have a value. Have a value. After theta bigger than x1 is what? Then become this. This guy out. I cannot taking out like white black bullets. Let me take this out, right? Then become 0 right here. When theta bigger than x1 is. What does that mean then? That means, hey, theta had nothing but what? MLE nothing but what? X1 is. This guy reaching the maximum point. So theta had nothing but x1 is. So that means your denominator, let me write it here. Okay, the denominator is nothing but x1. Okay, then the point is, looking at your numerator, I said supremum theta in alternative space, in null space, sorry about that, in null space. Your null space is composite, right? Going back to this, imagine that is, this is really ugly, so let me to show the new bigger graph. Right? Bigger graph right here. Okay, this is L theta given xi. This guy is theta right here as an increasing function until x1 is, right? X1 right here. Okay, then becomes 0. Okay. So imagine that theta smaller than theta 0 is my null space. Then become critical where theta 0 is then. For example, if your theta 0 is right here. Okay, good. That means the whole thing right here is your null space. Okay, then in that case, I don't have an answer for that. Is there something else I can help with? No. Okay. Okay. So then right here, if theta is right here, look at this picture. What's the MLE? X1 is my MLE. Right? So that means this guy right here, it turns out to be what? This guy is still x1. This guy is still x1 as well. That means what? Lambda x is 1. Okay? Then what happened? Hopefully I can take something out for you to see. Okay, good. Good. Oh, okay. I did not sacrifice much. It's x1 right here. What happened if this is my theta 0? Here become my null space. Does my x1 still qualify for MLE? The answer is no. Okay, because I'm looking for the guy maximize my MLE under my null spaces. Then who is the guy maximize my Laplace function under null space? The answer is what? theta 0. So that means right here, it's no longer x1. Right here become what? Theta naught. That means you have two options. You have two situations. One situation is if theta 0 bigger than x1, then you have that lambda x is 1. Okay? Another situation is you do have lambda x is what? Right here. Right here. Then if your theta not smaller than x1x. Okay? Good. So that means I think that's what I said right here. Okay. So if you say that this is the reason why you have this result here, really depending on where your theta now is. If your x1 smaller than theta 0, you have an identical numerator and denominator. So lambda x is 1. And then, of course, if x1 bigger than theta 0, then you have that proportion. You have that ratio right here. You have that ratio right here. You have this ratio right here. Okay. So then again, it's plug in theta 0, plug in theta 0, plug in theta 1 here. Okay. One is plug in theta naught, one is plug in theta, one is plug in x1, one is plug in theta naught. Then you do the ratio. You'll find this right here. Okay, you'll find this right here. And then again, it's this like ratio test, not as clean as a normal distribution case right here, right? This guy is really clean in a way, writing down lambda x more than c. Okay, this guy right here, really depending on where the theta now is. Okay, but by any means, it's you're still rejecting your null hypothesis x smaller than c. Whenever your test lambda x smaller than c, we're going to reject it. Okay, then again, it's I can rewrite this part right here, okay, to become this, okay, based on this guy. Again, what is c? We haven't found out yet, not found yet, okay. This guy's only general representation of your cutoff. We still need to find c. Then, after collecting the data, we know about x1. Then we need to know what c is. Then collecting the data to see whether or not my x1 is bigger than this guy. Bigger than that guy, bigger than this guy, reject null hypothesis. Smaller than that guy, then do not reject null hypothesis. Okay, so I think I can end up here. Okay, I got a question right here. Sorry about that. Okay, no, it's good. Okay, so then on Thursday we are talking about it. If I do know I do testing. Okay, again, it's much like the same thing as a estimator. It's if I do have estimator A, estimator B, then you should know how to compare about estimators, right? Compare MSE, mean square error, or compare variance. Okay, then right now it's still the same as what? You might have test A. Test A means I do have one rejection region. I have test B. I have another test region. And then how do I know which test is more preferable? Okay, so we basically use what? So-called power function to do evaluation of a test. Okay, so right here it's I do know you guys using beta for type 2 error before. Me as well. I don't know if we just study. I have beta type 2 error. Okay, but in my class, because we are using Kassenberger's textbook, they're using beta as a power. Basically, it's what? 1 minus of type 2 error rate. Okay, again, it's because the function of theta. Okay, theta could be in alternative space, right? And then by different value of theta, it's right alternative space. H1 right here. They have a different value of theta. So then, by different value of theta, you do have a different power based on what your testing region is, right? So that means again, it's power basically is what? Under alternative, theta belongs to alternative, right? Theta non-alternative. I reject it. I do the right thing. Okay. So yeah, 1:45 right now. Okay. So let's end up here, and then I will see some of you guys next hour. Okay, in the 673, and then if you have questions, you can speak up right now. I think we ended here. Yes.
Excuse me, Professor.
Yes. Yeah.
I have a suggestion about the display of the slides and notes.
Yeah. Mm-hmm.
I'm not sure if this could be I'm not sure if this could be better, but you may have a try. That there is a function in iPad called screen splitting.
Oh yeah, I do. Yes.
And if you could open up another notes app and write all the notes on that app, you don't have to write all the notes on the slides themselves.
Yeah, I tried that, but is that to become smaller? And first of all, let me try splits. I using my iPad to do everything, so let me try to see if I can. iPad share screen is not easy to use. I have to told you. So let me. Okay, so I do see that before. So I can split my share, right? Hold on. So I using host to screen multiple. You're saying the multiple participant could share screen. Is that what you said?
Maybe.
I'm looking my Windows version of Room. Only thing I can see is multiple participants can share screen simultaneously. So what you're looking for is want me to do it. One part of screen is slides.
Yes.
The other part of screen is my whiteboard, right?
Yes. Then you don't have to erase.
I'm worried about a whiteboard will be too small for me to write everything.
But you can scroll the notes app.
Right. So really, you want me to do it? I don't think using one machine could share two resources. Are you talking about one machine or two machines?
I'm not sure either. Just a suggestion.
Right. You might want to try a little bit to let me know. Yeah, another concern would be I may not have a really big whiteboard to write down, but I do need a big whiteboard to write down to show the formulas to you guys. Yeah. Well, let me just stop recording so they can convert to. Let me see.